Swayam Prabha. Digital India. Educated India.
Welcome to lecture 4 in the course of Manufacturing to Composites. So, in this lecture we will predominantly focus on how to evaluate the properties of composites. So, till now what we have covered is, we have covered introduction of composites, then we covered matrices, function of matrices, then we went into fiber, different forms of fiber, different fiber materials, and then we also found out the function of fiber reinforcement in a composite. So, now what we do is, we will get into the properties and understand little bit of composites calculations. So, in this lecture we will try to cover how to calculate the volume fraction, then we will try to cover the elastic behavior under longitudinal loading, then we will see the elastic behavior under transverse loading. Then we will try to continue with longitudinal tensile strength and transverse tensile strength. So, basically if you see, in elastic region and in plastic region, we are trying to find out properties for a given composite. So, the property of a composite are a function of the properties of constituent, phase and different relative propositions, size, shape, distribution and orientation of the dispersed phase tries to dictate the property of a composite. So, if you look into the geometrical and spatial characteristics of reinforcement in a composite, the concentration, size, shape, distribution, orientation plays very important role in deciding the property of a composite. The figure A shows two different concentrations. Basically, concentration here means the amount of reinforcement present in a composite. To a crude extent or to a large extent, it is called as a volume fraction. You can see, as the volume fraction increases in the bottom figure of A, you can see the properties change. The next is size. So, you can see a smaller circle and a larger circle. Smaller circle means it has larger surface area, lesser volume. So, it has more interface. So, this interface tries to enhance their wettability property or the adhesion between the polymer and the reinforcement. So, smaller the size, larger the surface area. Larger the surface area means, so you will have more surface area to come in contact with the polymer, more wetting, more interface, so a stronger composite. So, if you move to the next one is the shape, you can see there are two different shapes we have put here. These shapes influence the characteristics of the composite. Next one is the distribution. You have uniform distribution and non-uniform distribution of reinforcement. Non-uniform reinforcement, this is very common as far as metal matrix composite or particulate composite, ceramic matrix composite and all. It is a very common feature, wherein which the agglomeration happens in the reinforcing zone. So, all these reinforcements gets clogged or gets attached or agglomerated at one portion, and they do not have uniform distribution of strength across the composite. The last one is the orientation. So, you can see the orientation of fiber in two different directions. When you have orientation in different directions, it will try to give you different properties. Suppose let us assume whichever is in the horizontal line is 0 degrees and vertical lines which are there, which are referring to 90 degrees, then you will have different properties. The 0 orientation, if the load is taken along that direction, they will have higher strength as compared to that of 90 degrees. If you want to stack alternatively these two, then it will give a hybrid property. So, concentration, size, shape, distribution and orientation, all these factors add and play an important role as far as the property of the composite is concerned. Now, let us try to understand the volume fraction and weight fraction. The volume fraction and weight fraction are generally talked about in composites because they play an important role in deciding the amount of reinforcement added. Generally, when a manufacturing engineer talks, he always talks about weight fraction. A theoretician, or if you want to do a first principle theoretical calculation, we always talk in terms of volume fraction. These two are interrelated by density. Density is nothing but mass by volume. So now let us look into the model which we have developed for quantifying the properties. So here a suffix R, M, C refers to reinforcement, matrix and composite respectively. This is going to be common for all through the presentation of today's lecture, where big W and V are the weight and volume fractions. So these two can be interrelated by a term using density. Small w is called as the weight. So if you look at this W, whichever is there, that is W suffix M means the weight of the matrix is equal to W, which is weight of the matrix divided by weight of the composite, which is equal to R suffix M divided by R suffix C. So this R is the amount of reinforcement in the matrix and the reinforcement in the composite. This is multiplied by volume of the matrix. So this tries to give the weight fraction of the composite, next of the matrix, and if you want to find out the weight fraction of the reinforcement, what we do is we divide weight of the reinforcement divided by weight of the composite, which is equal to the reinforcement divided by the reinforcement of the composite multiplied by volume fraction. So I have given here weight fraction and volume fraction are related to each other through density. When the volume fraction of the constituents are known, then the same equation can be related as RC equal to R suffix of F, that means to say fiber multiplied by volume of the fiber plus R of suffix M matrix and volume of matrix. So this calculation came from the previous one, and when we wanted to do with respect to weight constituent, so we just do 1 by RC is equal to weight of the reinforcement divided by R suffix F plus weight of the matrix divided by R suffix M. This equation may be applicable to other properties of composite also. A very generalized equation is given here. So where X represents any particular property and the suffix C, R and M refers to composite, reinforcement, matrix respectively. So the next topic of discussion will be a model for quantifying the properties. So as we discussed earlier, there is a relationship between density, weight, that means to say weight fraction, and volume fraction. Going to our school days, we remember density is nothing but mass by volume. We just have to use this in this equation to find out a relationship between density, weight fraction and volume fraction. So let's start. M, which is the mass, total mass, it is nothing but mass of the fiber plus mass of the matrix. As I written earlier, mass is equal to rho into volume. This is volume. Okay. So this rho into volume can be written as rho of fiber into volume fraction of fiber plus rho of matrix into volume fraction of matrix. So this further can be written as rho of F into F, I will tell you what is F, into V plus row of matrix 1 minus F into V. So, row can be written as F into row of F plus 1 minus F into row M. So, here to convert the volume fraction, the volume fraction of fiber F to weight fraction of fiber, that is nothing but FW. We just need to establish a ratio between the mass of the fiber to the total mass. So, this can be expressed as F of W equal to M, mass of the fiber, divided by mass of the fiber plus, we write it as mass of matrix. So, this can be written as rho of F into FV divided by rho F into FV plus rho M 1 minus F into V. So, this can be further written as F rho of F divided by, this is suffix F, divided by F rho of F plus 1 minus F into rho of M. So, to convert weight fraction what is weight fraction? Weight fraction is FW to volume fraction F. What we need to establish a ratio of, what do we need to do? We need to establish a ratio of the volume of reinforcement to the total volume of the composite. This we have to do. So, to convert the weight fraction FW to volume fraction F, we have to just establish this. So, how do we do it? F equal to volume fraction, this is volume fraction plus volume fraction V of M. So, F can be written as mass by density, this is written by mass by density of fiber plus mass of the matrix by density of the matrix. So, this can be further simplified and it can be written as FWM divided by rho of F, that whole divided by FW, then M, that divided by rho of F plus 1 minus FW into M divided by rho M. So, this can be written as FW divided by FW plus 1 minus FW into rho of F by rho of M. So what did we do? We were trying to find out a relationship between density, weight fraction and volume fraction. These two terminologies are very important, and we know that there is a relationship between density, weight and volume fraction, and we have derived those two derivations in this slide. So we have written as mass. First mass we have written, then we have written it for volume. Mass can be represented by this. Then we assume that density multiplied by volume of the total composite is nothing but fiber plus matrix. So we have written it in this form. And then we have moved into volume fraction of fiber F to weight fraction of FW. How do we get it? Then we have gone to weight fraction to volume fraction. That also we have done. So by this derivation, we will be easily able to find out a relationship between the two relationships. So now let us keep moving further. The stress strain behavior, this graph I have already told, the stress strain behavior of fiber, matrix and composite. This is a stress versus strain graph. You can see the strain, this is for a glass fiber composite it is drawn. So you see there is not much of plastic elongation. So the fiber has very good E, and a composite whatever is in between the property of a matrix and then of a fiber. So sigma m is the matrix failure which happens. The sigma m is a point, sigma m star is the stress at the matrix which is taken here. So now let us try to understand the elastic behavior under longitudinal loading. So here what we are assuming is all the fibers are aligned in one direction and the loading happens in the same direction. Okay, the loading happens in the same direction, and we also assume that all the fibers take the same load. So here the final derivation, what we have done is the F of the fiber, the F is the load which carries by the fiber by matrix, can be represented by Lex. So let us also try to derive. So what are the assumptions I have made? Assumptions is I have assumed that it is a continuous fiber. And next, all the fibers are aligned in one direction. And I assume that the deformation of both matrix and fiber is same. So that means to say it is iso-strain condition. So the FC is the load which is carried by the composite, is nothing but is the load carried by the fiber by the load carried by the matrix. So this F can be written in terms of stress. So stress is nothing but which is F by A, force by unit area. So hence F equal to sigma by A. So now we know that SC into AC is nothing but S of F into A of F plus S of M, and it is A of M. What is this S? S is nothing but the failure strength. The failure strength is SC here. So SC is multiplied with AC, SF with AF and SM with AM. So to further proceed, we can obtain this equation, S of F into A of F by AC plus S of M into A of M divided by AC. In this equation, the total cross section area of the composite, we are dividing. This AC is the total. This AC is nothing but the total composite area. That means to say I am talking about the CS, cross section. Okay, since the composite fiber and the matrix length are all equal, since the fiber, composite and the matrix are equal. So we consider A of F by AC is equivalent to the volume fraction of the fiber, which is nothing but V of F, and A of M by AC is equal to the volume fraction of matrix, which is nothing but Vm. So SC can be written as S of F into V of F plus S of M into V of M. So it is assumed that the strains in the composite, fiber and matrix are equal. I said about isostrain condition. So S of C divided by EC is equal to S of F divided by E of F into VF plus S of M by EM into Vm. So when the deformation of the composite, fiber and the matrix is assumed to be elastic, so then sigma C by EC is nothing but EC sigma F by EF is equal to Young's modulus of F. Then sigma M by EM is nothing but E of M. So here we assume, what is the assumption? We assume that composite, fiber and matrix are assumed to be inelastic. Assumed to be elastic. Okay. What is E? E is the Young's modulus. This is Young's modulus. I write it down. E is Young's modulus. Modulus of elasticity. So which can be represented as EC is equal to E of F into V of F plus E of M into V of M. So by modifying this equation, what we finally get is modifying this equation, modifying, we get the EC equal to E of F into V of F plus E of M 1 minus V of M for the composite consisting of only fiber and matrix. These are all assumptions we make. So we assume that V of M plus V of M equal to 1. So because of that only we are able to get this thing. Thus EC is equal to E of F into V of F plus EM into 1 minus VF. So the composite modulus is equal to volume fraction of the fiber multiplied by Young's modulus of the fiber, Young's modulus of matrix into 1 minus VF. This is a very important derivation. You can expect some simple trivial problems to be solved in this using this formula. On similar lines, we can also do a ratio of loads carried by fiber and matrix. So the ratio of loads carried by fiber and matrix is given as F of F divided by F of M, which is nothing but E of F divided by E of M into V of M by V of M. So the response of the composite remains elastic. This proportion will be independent of the applied load. So here you should remember this point. Response of the composite, whatever we have taken for derivation, remains elastic This is independent of the remains elastic and independent of loading. Independent of loading. Higher the modulus, the volume fraction of the fiber is high, the higher will be the load carrying capacity. So, in this derivation, we have till now what we have done is two derivations we have done. One, we have done how do you find out a relationship between density, weight and volume fraction. How do you convert volume fraction into weight fraction? How do you convert weight fraction into volume fraction? Then we have seen a stress strain behavior of a fiber, matrix and composite. So, you can see fiber. So, now it is very clear, as and when you increase the volume fraction of the fiber, the strength of the composite also increases. So, we have derived this. We have derived the elastic behavior under longitudinal loading. We have taken assumptions. It is continuous, fiber is aligned and the deformation is isostrain, that means to say uniform strain. So, we have derived it and then we have proved it finally that the f of f, the ratios of the load carried by the fiber and matrix, we have found out, we have said f of f divided by f of m equal to Young's modulus of the fiber, Young's modulus of the matrix, which is multiplied by the volume fraction of the fiber and volume fraction of the matrix. So, now let us see the elastic behavior under transverse conditions. So, here again we consider it is a continuous fiber. So, again here the assumption is it is a continuous fiber and it is all the fibers are aligned at 90 degrees from the loading direction, So, here 90 degrees and the other thing is the stress in composites is equal to, that means to say uniform stress is applied, stress on fiber and this is equal to stress on matrix. So, that means to say S of C equal to S of F, which is equal to S of M. So, it is termed as, what is this terminology called as? Here it is isostress. In the previous thing we saw it was isostrain state, here it is isostress state. So, the deformation in the constituents or the composite can be written as the DC is equal to E of C into T of C. So, here I will write it in words so that you can remember it. Deformation in the matrix / fiber or composite is a product of strain and the corresponding cumulative thickness, So, DC is nothing but EC into TC. So, same way you can write DF is nothing but EF into TF and then DM you can represent it as DM into TM. So, finally what we write? We write EC TC is equal to EF TF plus EM TM. Why did we do this EC TC and all? Because all these things came into existence because of isostress state. So, clear? Because of this isostressed state it came into existence. Now, what we do is we try to take the TC aside. So, this can be rewritten as EC equal to E of F into T of F divided by TC plus E of M into T of M divided by TC. So, the thickness ratio, whatever we find out, the thickness fraction is equal to volume fraction for a given composite with uniform length. Okay, so this is nothing but EC is equal to EFF into VFF plus EM into VM. So when the constituents are assumed to deform elastically, the strain can be written as sigma by E. So this is nothing but, this can help in writing S of C divided by E of C is nothing but S of F divided by E of F into V of F plus S of M divided by E of M into V of M. So this can be written as, since sigma C is sigma F equal to sigma M, we can write it as 1 by EC is equal to VF by EF plus VM by EM, or we write it as EF into EM divided by VF into EM plus 1 minus volume fraction of EF into M. So what is this? This is equal to EC. So this is the relationship which is established for elastic behavior under transverse loading. So what did we see? We first saw the elastic behavior under longitudinal loading. Then we saw elastic behavior with respect to transverse loading. So the next topic of discussion is going to be longitudinal tensile strength. So generally what happens in a composite material, the failure mode is very complex. So first what happens is the matrix tries to play a role of uniformly distributing the load onto a fiber. Then the fiber starts taking a load. Then moment the fiber starts taking load, after some point of time the fiber fractures. Then it gets distributed. So it is not like a unique failure. What happens in metals is a phenomena here. So generally here there are several failure modes. So the modes that operates in a specific composite depends on both the volume fraction as well as the matrix property and also the interface property. When the failure strain of the matrix is higher than that of the fiber, then the fiber will fail before the matrix. Once the fiber fractures, then what happens to the load? The load is borne by the fiber is now transferred to the matrix. However, the matrix cannot take heavy loads for a longer time, so it also immediately fails. So now it is very clear that we are supposed to find out a volume fraction, that means to say a critical volume fraction which is required for the composite. So a certain volume fraction of the fiber will be the composite strength. So that means to say a critical volume fraction level we have to find out, so that we can have the strength properties taken by the fiber. So the volume fraction is called as a critical volume fraction. When you consider a composite which is made out of a fiber which is brittle and a matrix which is ductile, then it is very important to find out the volume fraction of the matrix. So this is a very critical equation. So we will try to see how do we get to this equation. So this equation is nothing but the ultimate strength of the composite, which is according to the rule of mixture. What did we study? 1 minus VF we studied in the previous derivation. This is called as the rule of mixture. So the ultimate strength of the composite, according to the rule of mixture, the fiber volume fraction is called as critical fiber volume fraction. So here this is very, very important, where in which you see the first term, which is nothing but SCU, which is nothing but the ultimate strength of the composite. SFU, which is the ultimate strength of the fiber. VF is the volume fraction. VF, volume fraction, which is given here, volume fraction. And S star M, S star M is nothing but the matrix stress at fiber fracture, at fiber fracture strain, which is nothing but EFF. So if you want to really derive this equation, so we can, in a real sense, in a real strengthening by fiber only when ultimate strength of composite exceeds the ultimate strength of matrix. So CSU is equal to CFU into VF plus SM star 1 minus VF, which should be greater than this. So in this equation, the critical fiber volume fraction must exceed the strength, the strengthening effect of fiber. So an effect by the fibers. So if we rearrange all these terminologies, what we get is V of F, that is V of F, which is otherwise called as V critical, which is SMU minus SM star divided by SFU minus SM star. So what is SM? SM is nothing but the matrix stress at fiber fracture strain, which is EFF. Okay. So the composite will not fail at a critical stress, which is derived here, The composite will not fail at the stress indicated in this equation. So after the failure of all fibers, let me go ahead. After the failure of all fibers, so what happens? All fibers fail. All fibers fail. Then what happens? The composite, that means to say the matrix, takes the load. The composite will fail at a stress. So what is a composite failure stress? Composite failure stress is nothing but V of M into S of M ultimate. So there is a decrease in strength of the composite on increasing the fiber volume content than minimum. So what happens is, if you see the strength versus volume fraction, there is something like a graph like this. So you are supposed to find out this point where you get a best benefit out of it, adding the number of adding the volume fraction to the composite, so that you get a very good strength. So what are we trying to do is, we are trying to find out this V min. Why is this V min? Adding more than this reinforcement does not play any major role. So the ultimate strength, of composites is when V min, when I think fiber we can say, when, okay, so I will rewrite it, ultimate strength of composite, when the fiber content, if it is less than V min, what we get is, see, ultimate is nothing but SMU 1 minus V volume fraction of F. So when the fiber content is more than V min, then what happens? Then SCU is equal to SFU VF plus S 1 minus V of F SMU 1 minus V of F. So we can say V min, that is V min is equal to SMU minus SM star by SU plus SMU minus SM star. So if you look at it, so this derivation is very, very important, which tries to talk about what should be the critical V, so to get the proper output. So if you go, if you plot it in a curve which is shown here, you can very clearly say this is the V min. What did we do is only this calculation. And you see here V critical, this is V critical, this is V min. We have found out the both. So this is for sigma C for a composite 1 minus Vc, and this is for sigma U. So this is for sigma with respect to ultimate in a composite, ultimate with respect to matrix. This is sigma, which is ultimate with respect to fiber. So this graph very clearly tells us there is a critical volume fraction for the fiber which you have to take, and there is a minimum which you have to take, such that you try to balance the load taken by the composite and by the matrix and the fiber. So when we proceed further, when we have to look for the transverse tensile strength, so in the transverse tensile strength, the strength of the continuous and the disc and the unidirectional fiber composite is highly anisotropic, and it is normally designed to take the load in the fiber direction. So during service condition, the transverse tensile load may also be encountered. So if you want to figure out this, so generally what happens in the transverse tensile load, there is always a prematured failure. Since the transverse strength of the unidirectional fiber is extremely low, there is always a prematured failure. So sometimes they say composite has a prematured failure. It is because that the loads are not properly balanced by the loads taken by the composite is not properly balanced. So in case of reinforcement effect, the fiber is sometimes has a negative effect if you load it in the transverse direction. So with this, we would like to come to an end for lecture 4. At the end of lecture 4, we will try to post some MCQ questions. You have to solve those MCQ questions and post it back the answer. So thank you very much.